Alright, here we go. We're going to work through example problem 19.1 from your textbook. That's on page 846. And we will be working through an acid-base buffer problem by first calculating what the pH of a buffer solution would be, and then calculating what the pH, what happens to the pH when we've added a strong acid or a strong base. So go ahead and leave yourself plenty of room. This one is going to be a bit longer of a problem, so bear with me. Feel free to pause the video and take any breaks you might need. I'll try and draw a line to show you the sections where you can take a break at. Let's go ahead and start with part A. Generically, what we're going to be doing for all this is calculating the pH. And so for part A, we're going to calculate the pH of a buffer that is 0.5 molar hypochloric acid, HClO, hypochloric acid, yep, and 0.60 molar sodium hypochlorite. The Ka value given to us for the hypochloric acid was 2.9 times 10 to the negative 8th. So it's a fairly weak acid. And just remember that the sodium hypochlorite is going to dissociate into Na plus and ClO minus, and it's the ClO minus that we're really interested in. The sodium's not going to do anything. So we just want to calculate the pH of this buffer solution at the very beginning. This is just a weak acid equilibrium problem that we've done a few times over and over again already. So let's just set this up. We're going to write our weak acid equilibria dissociating in water. So we have HClO plus H2O is going to form an equilibrium with forming H3O plus hydronium and ClO minus the hypochlorite ion. So we've got our Rice table. And so we're given the initial concentrations already. We're told that the hypochloric acid is 0.5 molar. And opposed to most cases that we've done before, there's still 0 H3O plus, but as opposed to most cases that we've done before, there hasn't been any of the ClO minus or any of the conjugate base. But in this case, we are actually preparing the solution with some of that conjugate base around, and we're told it's 0.06 molar. So we can go ahead and add that in. Now we may look at this and say, well, there's already some of the product that is going to be formed. This reaction might want to go in the reverse direction. But we should be careful that since there is still no H3O plus, Q is still equal to 0, the reaction proceeds to the right. So it's still going to try, the HClO is still going to try and dissociate a little bit and produce some of the H3O plus, even though there's some of that ClO minus there. Now, important point here is that because there was already some of the ClO minus, some of the common acid or common ion already present, it is going to suppress ionization of the acid. So again, to repeat, because there is still some of the hypochlorite ion there, the HClO can't dissociate as much because it's going to be producing some of that ClO minus that's already there. But it is going to dissociate a little bit, and so we'll go ahead and write those in. So at equilibrium we have 0.5 minus x, and 0.60 minus x. We always ask ourselves, what is Ka in this case? It's always products over reactants. And so we'll have H3O plus and the ClO minus over our HClO. We can go ahead and plug all these values in. We know Ka is 2.9 times 10 to the negative 8th. And that's equal to, concentration at equilibrium for the hydronium is just x, and that's going to be multiplied by 0.60 minus x over 0.50. Oh, sorry, I made a mistake. Let's go back here. This is plus x, so 0.60 plus x, and this would be 0.50 minus x. Now we're all good, and it's not going to matter that much because we're just going to assume both of these are small. So this simplifies it down, and we're left with 2.9 times 10 to the negative 8th is equal to x times 0.60 over 0.50. Now we want to solve for x, so let's bring this down here. Remember, x in this case is equal to the concentration of H3O plus, which ultimately is our goal because we need the pH. So once we've calculated the hydronium concentration, we can take the negative log of that and get the pH. So we're just going to rearrange this and solve for the H3O plus right away. So this becomes 2.9 times 10 to the negative 8th, and all I'm going to do, let's go back to this equation over here. I'll write this in green. We're going to multiply by 0.50 and divide by 0.60. That's going to cancel out the right side, and we're going to do the same thing to the left side over here. We're going to multiply by 0.50 and divide by 0.60, and that's going to rearrange this and solve this for x for us. And once we've plugged this all into the calculator, we end up with the concentration of the hydronium, H3O plus, is equal to 2.4 times 10 to the negative 8th. Very small number. It dissociated very little. We could go back and double check that our 5% rule assumption is correct, and you should do that on your own, but I will tell you right now it's probably correct. So we simply just need to calculate the pH. Remember, the pH is always the negative log of the H3O plus concentration. So pH is equal to the negative log of 2.4 times 10 to the negative 8. And we end up with our pH is equal to 7.66. A little bit of a critical thinking check. So we'll call this critical thinking check. This solution is basic. Its pH is above 7. It's only slightly above 7, but it's above 7. And remember that at neutral pH, the concentration of H3O plus is equal to 1 times 10 to the negative 8th. And in this case, our concentration of the H3O plus was 2.4 times 10 to the negative 8th, meaning we have less H3O plus around at equilibrium. So it makes sense that this solution should be basic because there is less H3O plus, meaning that at equilibrium there would be more OH minus, more of the hydroxide, which would drive the solution to be basic. Remember that H3O plus times OH minus always has to be equal to 1 times 10 to the negative 14th. So since our H3O plus is smaller than it normally is at equilibrium, and again I made a little mistake, it's smaller than it is at equilibrium, this solution needs to be basic, and it is. So that's kind of our little quality control check. Critical thinking check. Let's go back here. So we're going to take a quick break before we start part B. So go ahead if you need to finish up your notes. I'm going to set up part B here real quick, but I'll leave this as one continuous video. I told you it's going to be a bit of a doozy. For part B, I want to know the pH after adding 0.020 moles of hydroxide, so NaOH, sodium hydroxide, to 1.0 liters of buffer. So the way this problem has been set up is that in this case, let's move this up here, in this case we're just adding some solid sodium hydroxide to a given amount of buffer. So the volume of the buffer is not changing. So let's just make a quick note. In this case, hydroxide, and that's the part we care about, sodium's not going to do anything. Hydroxide is added as a solid. Volume does not change. In part C, we're going to see when we add the acid component, we're going to be adding a liquid acid, and the volume will change, and we'll kind of readjust as we get there. But for now, we just assume the volume doesn't change. That means we can just work in molarity still and calculate the concentration of the hydroxide. And that's simply just the moles per liter. So we have 0.020 moles of the hydroxide over 1 liter. So this is simply just the concentration of hydroxide is 0.020 molar. So now this is the part where we're adding a strong component to our buffer. So the first step is the upset. So now our buffer has reached this equilibrium condition, and until now it's just been hanging out. That's the part we did in part A. We just let this reach equilibrium and calculate what the pH was. Now we're going to be adding a strong base to this, so we're upsetting the equilibrium, and the base is going to react with the acid component of our buffer. So we're going to say our HClO, our hypochlorous acid, hypochlorous acid, is going to be reacting with the hydroxide. And again, because hydroxide is the strongest base we can have in water, this essentially goes to completion, doesn't form an equilibrium, it's just going to go all the way to the right. And this is our acid, and this is our base, so it's going to accept a proton. The acid's going to donate a proton, so we get water and the hypochlorite anion. So this is the conjugate acid and the conjugate base. So again, let's just make another little note here. Notice the strong component reacts completely. So we'll set up our little rice table here. Now this is a bit misleading because we already know the change in this case. All of our hydroxide is going to be reacting. But we kind of keep this same flow because we're going to be using this rice table in just a second for the reset part. So the initial concentration, this is the same buffer we were using before. So we can use the concentrations from before. We have 0.50 molar of the hypochlorous acid, and we added 0.02 molar of the strong base hydroxide. We don't have to worry about the water, and the conjugate base started off as 0.60 molar. Now again, because we're adding the strong component and this reaction is going to proceed to the right no matter what, we can just say because of this strong component, the hydroxide, this reaction is going to go all the way until there is no hydroxide. So we know what the change is. We know we're going to lose 0.02 molar hydroxide. So that means at equilibrium, we know we have 0.48 molar of the hypochlorous acid. There is now 0 hydroxide, it reacted completely, and we get 0.62 molar of our conjugate base. And so now this leads us to step 2, the reset part, where now we're going to watch how our weak acid equilibrium resets itself. So we just draw out our weak acid equilibrium. This is going to require another rice table. So now at equilibrium, we just take these values we just solved for. I knew it was going to do that to me. Let's see here. Okay. Let's just write these in really quick. So at equilibrium now, we've upset this equilibrium. Now we're going to watch it reset. So notice we just took the values at equilibrium from the first step and moved these down here. And we can just plug these in. Now again, we don't know what the change is going to be, but because there's no hydronium around anymore, or at least there's very, very little, this reaction is going to proceed to the right. We don't know how much, but we know it's going to go to the right. And we're going to end up with this equilibrium. We should be getting pretty used to doing these equilibriums by now. And again, we ask ourselves Ka. What is Ka? Ka is equal to the concentration of the products over the reactants. We know all these things now, so we can just plug it in. 2 times 10 to the negative, 2.9 times 10 to the negative 9, 2.9 times 10 to the negative 8th, is equal to, at equilibrium we have x, 0.62 plus x over 0.48 minus x. And again, we just assume x is small. That leaves us with 2.9 times 10 to the negative 8th is equal to x times 0.62 over 0.48. And again, I want x because x is my H3O plus concentration, and ultimately we're trying to calculate the pH. So I'm going to multiply both sides by 0.48 and divide by 0.62. And this all simplifies out to, remember, x is equal to our H3O plus concentration. And that's going to be equal to 0.48 over 0.62 times 2.9 times 10 to the negative 8th. And we crunch this out on the calculator, and we get x is equal to 2.2 times 10 to the negative 8th. And again, that's the H3O plus concentration. We want to know the pH, which, as you should be getting used to now, is the concentration of the H3O plus, or the negative log of that. So we come over here and plug all this in. Our pH is equal to the negative log of 2.2 times 10 to the negative 8th. Running the final numbers, we get a pH of 7.66. So let's just review really quick. If we go back and look, oops, of course. Let's go back part A really quickly, excuse me. This is 7.62. I was reading the wrong value. Now this looks good. So if we compare our initial pH of the buffer before we added anything, it was 7.62. Now it's 7.66. Again, just a quick critical thinking, CT check. We added some hydroxide to it. The pH should go up a little bit and get a little more basic, but it shouldn't get that much more basic. And sure enough, it didn't. It only went up by 0.04 pH units, which is pretty good. So our buffer is resisting a change in pH. Again, we'll take another quick break before we start the last component here, part C. Okay, part C. We want to know the pH after adding 30.0 milliliters of 1.5 molar HCl to, now we're going to change the amount of our buffer, 0.5 liters of buffer. And as I said in part B, now we're changing the volume because we're adding a liquid component to our buffer, so we're going to be increasing the volume. So we have to calculate new concentrations. We're going to be diluting all of the components. So we calculate new concentrations. And we're going to do that using our good old dilution equation. M1V1 is equal to M2V2. And in this case, M2 is going to be the initial molarity in all of our reactions that we're going to be doing. So if we rearrange this, we say the initial molarity, or M2, is simply M1 times V1 divided by V2. So V2 in this case, we'll come back over here to the left. V2 is we're taking 0.5 liters and we're adding 30 milliliters, which is 0.030 liters. So our new volume, V2, is just 0.53 liters. And we can calculate the new concentrations from there. So our initial concentration of the HClO, we started off with 0.50 molar, that's M1. And we had 0.50 liters of that. And the new volume, V2, was 0.53 liters. So our new molarity is 0.47 molar HClO. repeating this process for the ClO minus initial concentration. At the very beginning of all this, before we mess things up, we had 0.60 molar, and we had 0.50 liters of that. And now the new volume is 0.53 liters. And again, the new molarity of this would be 0.57 molar. And finally, we're even diluting the HCl that we're adding. And remember, the HCl dissociates completely, so we're going to have actually just H3O+. The new molarity of that would be the 1.5 molar we started with, and the 0.03 molar that we added, or sorry, 0.30 liters that we added, and the new volume of 0.53. And this leads to a new molarity of that as being 0.085 molar H3O+. Alright, so now we have the new molarities of all the components. Let's see what's going to happen. The strong component, the strong acid here, H3O+, is going to react with the weak conjugate base. It's not going to react with the weak acid. That wouldn't make sense. Acid plus acid doesn't happen. But the acid and the base are going to react, so let's draw that first. That's our upset. It's the strong component reacting with the conjugate weak base. So we have ClO minus plus the H3O plus. H3O plus is the acid, so it's the strong acid, so the reaction is going to go to the right. And we're going to form, it's going to donate a proton, so we're going to form HClO and water. So we'll set up another rice table here. And again, we know these initial concentrations, we just calculated that, so the ClO minus is 0.57, H3O plus was 0.085, and the HClO was 0.47, and water doesn't matter. Now again, because the strong component of H3O plus is going to force this to go to the right completely, we know what the change is for the upset part. It's a stoichiometric reaction, meaning that all of that H3O plus is going to react. So we lose 0.085 molar. And so we lose 0.085 molar, and we gain 0.085 molar over here. So now that at equilibrium we have 0.56 molar of the HClO, we have 0.48 molar of the ClO minus, and we have 0 H3O plus. Again, now we've upset our weak acid equilibrium, so it's going to reset itself. And we are going to calculate how it's going to do that. So we just draw out our weak acid equilibrium again. Again, this is just the generic form of HA plus H2O. It gives us H3O plus and A minus, except HA and A minus are HClO and HClO are ClO minus. And now we have to be a little careful here because the HClO came from the product side of our reaction over here. So we actually have 0.56 molar, and the water doesn't matter. There's 0 H3O plus around, and we had 0.48 molar of the conjugate base. So we have to be a little careful because they've swapped sides here. And again, because there's no H3O plus, this reaction has to go to the right to generate some H3O plus. We end up with 0.56 minus X, gained X, and 0.48 plus X. As usual, we set up our weak acid equilibrium. Ka is equal to H3O plus times ClO minus. This should be getting automatic at this point, and HClO. This is still equal to 2.9 times 10 to the negative 8th, and that's equal to the H3O plus concentration X times 0.48 plus X over 0.56 minus X. And again, we assume X is small. And again, we remember that X is equal to the concentration of H3O+. So I'm going to skip a step here in the rearrangement. This X is going to be equal to 2.9 times 10 to the negative 8th times 0.56 over 0.48. We end up with X, again our H3O plus concentration, is equal to 3.4 times 10 to the negative 8th. We want to know what the pH is. That's equal to the negative log of the H3O plus. So plugging all this in, pH is equal to negative log of 3.4 times 10 to the negative 8th. Our final pH, we made it all the way through, 7.47. And last time, critical thinking check, CT check. So we've added a strong acid now, so we added 1.5 molar HCl, so that's our strong acid. It dissociated to make H3O+. And relative to the pH we started with 7.62. Relative to that, the pH has gone down a little bit, down to 7.47. So that makes sense. We added an acid, the pH should come down, it gets more acidic or more towards neutral. That's it for problem 19.1.